students, welcome to session 7 of our course Operations Analysis, where today we talk about integer programming. So the content of this short video is today's topic and learning objective, and then we dive into integer programming and the characteristics of these specific models. We will also consider special constraints that require decision variables to be integer, which is, for instance, k out of n constraints, or the quite famous Knapsack problem of operations research. So the content is that we look at integer programming, so problems where we require the decision variable to be integer. We can make this even more fierce and look at or force our decision variable to be binary, so 0 or 1. And then we look into models that require decision variables, just some of them, to be either integer, binary, together with decision variables that can also be continuous, like in linear programming. So the learning objective of the session is to learn about these problems, to learn specifically how to transform these models or LPs that we have seen beforehand in this type of problems, where we can use them for, and then also and specifically how we can implement them using, for instance, Excel or also AMPL. So in integer programming, it is a restricted form of linear problems where we reformulate the decision variables and we require them to be integer, or we could also require them even more restrictive to be binary. That means that they just get either the value 0 or the value 1. That is like requiring a yes or no decision, like we have seen in assignment problems. So as examples where we can use these models for instance, if we have a design task where we need to design a production and distribution network, then with these kind of models we can respond to the question if a certain plant should remain open or be shut down, or if a new one needs to be built and where, or if a certain distribution center should be opened or closed, like in supply chain management, or as we have seen in our network-based models, where we should route some trucks from location 1 to a location 2. So which route shall we select for that? And then another variant is where we mix certain of these decision variables together, where we require just some of them to be, for instance, binary, or some to be integer, and others that can remain continuous. And I will show you a very nice and quite useful problem that is called the capacitated lot sizing problem. That is very useful for when to decide how much to produce and when to produce it and how much to put on stock. So let's first of all take an example. We have here given some data for the California manufacturing company, and they want some questions to be answered. They want to know where to build a particular facility that requires a certain investment. A warehouse should be located together with a factory, meaning that a warehouse should not be built together with another warehouse, so it requires a factory to be built in the same place. Each of the facilities gets an attribute of the decision variable that is either 0 or 1. So the objective here in this problem formulation is that the company wants to maximize the net present value and remain within the limits of available capacity, that is in this case $10 million. The mathematical problem can be stated as follows. That makes it also easier to be implemented later when we use Excel or AMPL. We have a maximization. We maximize objective function zeta, subject to the net present values multiplied by the decision variables from x1 to x4. And now what is interesting is if we look at the constraints, that the first constraint that we see here is to remain within the available capital. So we have a cost associated with a building or not building of a factory, of factories in this case, and with respective warehouses. Then we have given the task that, or the requirement that a warehouse should not be built together with another warehouse. Then we have the requirement that a warehouse is built in a location where there is a factory, because both decision variables are binary, so 0, 1. We want the factory to have a value of 1, so here would stand -1 if the factory is built. And in that case, when a warehouse is also built there, then these two would become 0. So the decision yes in these cases then would we require that we have a value of 0 here. And the same is valid for the factory in, I think it was Los Angeles, yes. What is more now, we have the decision variables, and here they are defined to be larger or equal to 0 and smaller or equal to 1. Or better said, while here it's the decision variable is formulated to be integer, but we can also replace these two constraints and require it to be binary. That is more straightforward. So let's have a look at how we can model this problem. So here I have given the decision numbers, then the net present value of the different decisions, and the capital that would be required for them. So for the first thing that I define is my decision variables. And as always, I give it a code, so I remember where I define them. And now what I require them of all decision variables is that these should be smaller or equal to 1. So, well, I want to know how much I need to invest if I invest in all of the decisions, or if I build 2 factories and together with 2 warehouses, and we see that this would give a total capital required of 16 million. But we have available only 10. How much would I use as capital? And therefore I want to have the sum product of the decision variables together with the required capital. So how much would I use? And this should be smaller or equal to the available capital. And now what we need to consider is the constraints that we have given. So the first one that I just defined would be the constraint 1. About the capital available here in the first constraint. And now I need to define the other ones. So constraint 2, give it a little bit of order. Constraint 2 says now that we just built we don't want to build two warehouses, so building one of the warehouses exclude that we build the other one. We have x3 plus x4, and this should be smaller or equal to 1. So we have mutual exclusiveness. Then we have constraint 3. And here, just to use the color scheme, I put every cell that is calculated in green. And here, for the other constraints, we will have smaller equal to. So I can just copy them. And now let's look at constraint 3, just to not mix up again. We have minus x1 plus x3 is smaller equal to 0. And the same is valid for the fourth constraint. So constraint 3 is minus 1 plus x3 here. And then we have minus x2 plus x4, and this should be smaller equal to 0. Now we are missing the objective. We want to maximize net present value, so we say some product of the coefficients for the net present value of the decisions multiplied by the decision variables. Yeah, so now we go to the solver, and we say that our objective should be maximized by varying the yellow cells where we find our decision variables. And now the constraints are that for the first one was that we use just the capital that we have available. So we cannot use money that we don't have. And then we can add our calculated constraints. That should be smaller or equal to the right-hand side. And now another thing that we need to require is the decision variables to be smaller or equal to 1. And what is more, we want them to be integer. Now, as usual, we want to require them to be non-negative, and we want to apply the simplex algorithm. So let's see. So we have found a solution. Everything is, the solution is optimal. And if we have a look at our result, we see that we use 9 million of the 10 million, and that our objective of the net present value is $14 million. And here in our decision, we see that we decide to build the 2 factories in Los Angeles and in San Francisco, but we do not build any warehouse. Let us see now how to implement the California company problem in AMPL. I show it to you from the very start. So the first thing that we will do is we create the model file. So we call them Calif because we don't want to write so much, and we need the file extension mod for model. Then let's stick with the model formulation first. So the first thing now that we need is the parameters and the sets that we are going to use for our problem. And I want to define first the set of investment alternatives. You can call them how you like. And these are the set of investment alternatives. Now we need two parameters, one for the net present value and the other one for the required capital for the decision alternatives. So we say parameter NPV. And this now pertains to our set of investment alternatives because it is one attribute of our investment alternatives. And we define the net present value to be larger or equal to 0. So the next parameter that we define is the required capital. And this is also an attribute to our set of investment alternatives. And we also define it to be larger or equal to 0. And now we need also the parameter to how much of capital we have available. So we define available capital. And also this one should be larger or equal to 0. And we also write some comment to it so we recall what we intended with the parameter. So this is the total available capital for investment. And now we define our decision variable. I call it invest. And also this one pertains to our investment alternatives as it is the selection of these. And also this they should be larger or equal to 0. And what is even more now, we want to define them integer. Our decision variable. Now I define the model. We have a maximization problem, so first we define the objective function. So we want to maximize investments. I call the function investments. You can call them however you like. So now we sum over all our investments. I use the index E. And this is now our set of alternatives that we have available. So we have E in investment alternatives. And now the objective function is the NPV of these of one decision alternative multiplied by our decision variable that is called invest. And now we need our 4 constraints, at least 4. So we define subject to, and now first constraint was the available capital limit. So capital capacity, I called it, and we sum over all our investment alternatives. And now the constraint is that we take the required capital for the decision alternatives and we multiply it by the decision variable, and we require it to be smaller or equal to our available capital, which is a single parameter, so no index. So that was our first constraint. Now the second one is we had the mutual exclusiveness of building 2 warehouses. So I call it mutual exclusiveness. And that was that our investment, the decision alternative 3 and 4 should be smaller or equal to 1. So we take our decision variable, and now comes something that is not my favorite, because we hard code these variables. Normally you want to have it as flexible as possible in your model, so you don't have to remember the different requirements in this case, but or you want to define everything over a data file that is then more flexible, so you don't hard code anything. But in this case we just do it. So here at most 1 new warehouse should be built. Now our third constraint, that was the contingency. That a warehouse is just built in a location where we have where we build also a factory. So we have the investment 1 minus investment 1 plus investment 3 was required to be smaller or equal to 0. And the same now we spare some time in copy pasting for the other location in San Francisco, and that was a minus investment 2 plus investment 4 should also be smaller or equal to 0. So a warehouse in San Francisco is built only when a factory is built there. Yeah, that was it so far. Now we need another constraint that requires all our investment decisions to be smaller or equal to 1. So we want to force the model to just use once the selection of an investment and not 3 times, for instance. So selection of investments, and this is now required to be E in investment alternatives is our investment decision to be just made once. So it's either or. Well, if we would require, and this is now twofold, or there are multiple ways of doing, of modeling it. So we could add first this constraint as I did it. So we can either use this constraint, or we could define our variable as binary and then we would have for our small model the same effect. But well, if we have very many decision alternatives that can be made, we might want to add the constraint and not to require the variable to be binary for computational reasons. The data file, and I call it Calif for California. And to highlight now certain data, we can start with writing data here. And now the first thing that we want to define are the parameters, and we do define now the net present value and the required capital for our decision alternatives together. So we write param and then double point NPV and required capital should be double point equal, and now I do my documentation. This is, and not to forget the semicolon. And now we need to define the available, did I forget anything? Available capital, that is just an input factor of 10 million. And that's all what we need to do here. Now, because we want to spare some writing, we write a run file, calling it Calif as well. Now we define that the model that we use is Calif mod. Data is given by Calif dat. And what else can we write? We could write that we want the option of the solver Cplex. Then we want to solve the problem, and we want to display investments and our decision variables that are called invest. Let's see if I made any typo. So now we invoke AMPL with include Calif run. Let's cross fingers. And I made a mistake here, as you can see. And that's always nice, because then we learn something. So we see here the available capital is not a parameter or variable constraint. Okay, so that was one mistake in the parameters of invest alternatives. So what I'm going to do is, when I state my data as I did in the data file, then I can add the parameter of the decision alternatives, and I define an index n, that is the index for investment alternatives. And then I define also here that our investment alternatives are given by a list from 1 to the index n. That is one thing. And the other thing is that then in the data file I define the parameter n as containing 4 decision alternatives. And now our model should work. And we see that we have a solution. The objective is 14. We have used 0 MIP simplex iterations, 0 branch and bound nodes, and our investment is 14. So here we see also now the decisions on the investment. So we built a factory in LA, one in San Francisco, and no warehouse. So what we have seen now with our implementation is the use of binary variables and integer variables in our models. We can use them to build an yes or no decision, or to reformulate an original problem and transform it into a binary integer problem, or we can also use it for integrating it into mixed integer problems, so both having both the continuous variables as well as integer variables. So now when we consider either/or constraints, we want to make the choice between two or more constraints, in this case just two, where we want to impose to the model that just one of the constraints must hold and the other is not selected. For this example, we take our plants, the third plant and the second plant of our Wyndor glass example. And now we want to impose that just one of these two holds and the other one is free for another purpose. So we can do this by modifying the right-hand side and adding a new term to it, which is composed by an auxiliary variable that we define to be binary, so the selection 0, 1. And we multiply it by a huge number so that the right-hand side here, if the constraint is selected, becomes huge. Let us consider how we can do this in Excel. So this is the original model that we have used for Wyndor glass. Now we define the auxiliary variable epsilon. In this case, it's either or the decision between these two constraints, so we just need one epsilon. And we need now to modify our constraints accordingly. For the first one, for plant 1, nothing changes. But for the second one, now we add to the right-hand side the named term. So we multiply a big number, which I will denote here in this cell, multiplied by the auxiliary variable. And here I denote the big number, which I choose to be 1000, also for the other one. And this is now calculated, so I use the usual calculation scheme. And for the first constraint, as said, nothing changes. The second one, as stated in the mathematical model, adds the new term. And for the third constraint, we do similar. We say 1 minus the selection of the epsilon multiplied by our big number. And we check if that holds. So now we have the selection 0 of epsilon, meaning that here this constraint is selected for the plant 3, and if we change that to make the selection for plant 2, then we see that not much is happening. So now we see that this changes. So what we need to do now for the solver, we start from scratch, as this is a new sheet. So we define our objective to be in this cell. We want to maximize the problem, the objective, sorry. And the changing variables are denoted as usual, but now there comes something different because we also change the epsilon variable. Next thing, we define the constraints. As used should be larger or equal to our new right-hand side. That also contains the selection of the epsilon variable. And we want to define the epsilon variable to be binary. And then the decision variable should be positive, and we use the simplex to solve our model. We did everything correctly, so we found an optimal solution. And if we look at the solution, we select the plan 2 with respect to the constraint and not the third one, and we have a total profit of 45. And we see the selection that we produce 9 windows and no doors. We can generalize this selection process from either or to consider more than just 2 constraints of the problem. So we could say that we want to consider a certain selection of constraints of the overall problem, but not all of them. So we take just k out of n constraints into account. And the mathematical formulation in general terms looks like this. Here we have the left-hand side of the constraints with the problem smaller or equal to right-hand side denoted by d1 to n. And we do the same as we have done with the either or. We add a new term that is the auxiliary variable multiplied by a huge number to be added to the right-hand side. And then we need to define that our auxiliary variables that we have constrained to be binary need to be equal to the overall selection of the constraints. So if we have a set of, in the model of 10 constraints, and we select just 8 of them, then our auxiliary variables in sum need to be also 8. Let's see how we can use this now for our problem of the Wyndor glass company. They have a new requirement. They say that they have 18 hours of production time per week in Plan 3. And this is currently unused, as we have seen beforehand. And now for our new available products and future ones that would be ready soon, we want to make this available. So in order to leave the remaining capacity unused for future blocks, we want, or the management wants to know now how much production time should be made available for these new products, and if it should be 6 hours, 12 hours, or 18 hours per week. So that we can reformulate the third constraint for Plan 3 now, and we modify it as follows. This was our normal left-hand side, and now we want to make the selection if the right-hand side should be 6 hours, 12 hours, or 18 hours, and we need to constrain our auxiliary epsilon variable to make the selection between these hours, so the sum of them should be just 1, and we define it as binary. So this is our original problem. Now we want to modify the right-hand side for constraint 3. So we take into account these different hours available for Plan 3. And they are now, the selection is 6 hours, 12 hours, and 18 hours. And for that selection, we define the auxiliary variable epsilon. Let's make it look nicer. For the other 2 constraints, everything stays as it was. And now we need the restriction of the auxiliary variables to be in sum just 1. So if we sum them all up, then this should be no larger than 1 as a requirement. Anything else? Here we need to add that now the right-hand side is the sum product of the selection of the hours available and the auxiliary variable epsilon. For the solver now, the data that we give to it is as follows. We have given the objective here in this cell. It is a maximization problem. This does not change. Then we want the yellow cells to change. These are still continuous variables. And we want also the auxiliary variables to change. So we define that these cells would change. And this is now to be deleted. So I start new to give the constraints over. The first constraint is that the hours used should be smaller or equal to the hours available. This did not change. Then I want to define our auxiliary variables to be integer. And now I constrained the selection of the hours made available for plant 3 to be just 1. Everything else is as we know it. And now we see that we have found an optimal solution, and that we select for plant 3 the hours available of 18. Another famous example of integer programming is the so-called knapsack problem. We have a knapsack that can contain a certain maximal amount of weight, and we want to fill in some items that come along with a value to us, but also with a certain weight. So we have 2 attributes for our items that we want to put in the knapsack. So we have n different types of items that we deem desirable to take with us. For instance, a bottle of water on a hiking trip, an apple, an orange, a sandwich, and so forth. And well, they come along with a weight or also volume that limits us to take them all, because we have given a certain maximum amount of weight that we can carry with us, or volume. And now we want to figure out how to load our knapsack with which combination of items that we want to take with us in order to maximize the total value of our knapsack. The mathematical formulation looks as follows. We have a maximization problem, and we sum over all items, their value, and we multiply it with the selection of these items. And this is the capacity constraint. So we sum over all of our items, their weight, together with our selection of it, and this should be not exceeding a certain amount of weight. For our decision variable, we define it to be binary. So we make a selection to take an item or not to take an item with us. Let's have an exercise with the knapsack problem. We want to go on a trip and we want to take a flight with an airline that allows us to take a number of 3 kilo with us in our luggage. We want to take a set of things with us that do not exceed the total number of 3 kilos that we can take. We have a weight associated with the items that we want to take with us, and we want now to decide what to put in our luggage. This we do in a way that we don't exceed this 3 kilo limit. We have a list of items given that are listed here from A to J. They are associated with the weight and with the value to us. And now I show you how to implement this in Excel. For the demonstration of how to implement this in Excel, we have copy-pasted the data now of our knapsack problem into Excel. And the first thing that we do is we define the changing cells, so where our decision variable should be placed. And I use my usual color scheme for that. So now what we also need is the calculation of the total weight for the items that I take with us, we take with us. This is a calculation, so I mark it in green. And now we multiply some product, the weights, by the selection of the items. Let's try out if that works. So we just look if the function is working, and it does. And this weight now shall not exceed a maximum weight given. And I forgot to highlight this on the slide. We are flying with a very nice airline that allows us to take a maximal 100 kilo with us, despite the normal 23 kilos. And the next thing that we need is the objective that now should maximize the value of the items we put in our luggage. So we say sum product is the value and the selection of items. So now we are set to give over the data to the solver. Our objective is given in the cell. We have a maximization problem, and we have the decision variables given here that I immediately constrain them to be to be binary. And the next thing is the constraint that our maximal kilo are not exceeded. So the items that we take with us are not exceeding the 100 kilo that we are allowed by our airline. Then we use the decision variables to be non-negative, and we use the simplix to solve the problem. And we have done everything correctly, so we see that we take 4 items with us, and we reach the maximal allowed kilos of 100. Now I show you how to implement the knapsack problem into AMPL. For that purpose, I write a new file that I call KS for knapsack. And let's start immediately with formulating the problem. So the first thing that we need is our set that contains the items that we want to take with us. So we define set objects, and I documented I want to give it the index k, and it is a list from 1 to n. We need now 3 parameters that are the weight, the value of our object, and the parameter of how much we can take with us, so the maximum amount of the weight or the capacity of our knapsack. So we write parameter weight, and this is now an attribute to objects. And we want to catch some errors, possible errors, so we define it to be larger or equal to 0. The next parameter is our value. This is also an attribute of the objects. And here we do the same with respect to error catching. And now the third parameter is the capacity of our knapsack. So we write capacity. And this is a simple input parameter. So no indexing. And now we define the variable. I define it as x, our selection of items, x items we want to select. And now I define our decision variables to be binary. And we are set to state our model. First thing is our objective function. We maximize the total value of our knapsack. So maximize total value. And that is given by the sum of objects that we take with us. So the sum over k in objects. That is given by the value of the items k multiplied by the selection of these items. And this is subject to the capacity constraint limit. So subject to capacity limit, which is given by the sum of the items that we put into the knapsack, given by the weight of the single items multiplied by our selection. So this is all with respect to our model. Now we define our data file, ks. And we want to highlight the data a little bit more nice, so that we see what is a list and what are our parameters. I define data. And now we need the list of the weights and the values of our objects. And for that reason, I take the list from Excel and transpose it to become a list as follows, that I can simply copy-paste into AMPL. Now I need some modifications. So this is a parameter of objects. And because AMPL is case sensitive, I need to state the set of objects exactly the way we have done it in the model. Now we have list items that are weight and value to these objects. So we need to add 2 double points for the parameter and the object that are now characterized by the weight and the value. So I denote the table with double point equals to our list A to J for the items, and I finish the table with a semicolon. The last thing now that is missing is our maximal capacity parameter, and this was 100 kilo for the very nice airline. This is all that we need for the data now, and the last file, because we don't want to write so much, is the run script for AMPL. That is model ks mod now data ks data that we use. Now we could give it some more information about the solver, but I won't do that. The solver will be selected from AMPL due to the definition of the decision variables. So we say simply solve. And now we want the table to look a little bit nicer. So we take the option display in a more compound list. So one column list as follows, and I want to display the decision of the items that we take with us, and I want to know how much we are using in terms of weight. So I sum over k in objects the weight multiplied by our decision. Okay, now we are set. So we invoke AMPL by say include ks run file, and I made an error, and I just was made aware that you have figured it out already. I forgot something in our capacity limit constraint, because I forgot to tell AMPL that this needs to be smaller or equal to our total capacity, and then things do not work the way they should. So now I hope we are all set. We don't normally need the option solver Cplex, but I added it now to the model, through the run script. So I say include ks run, and crossing fingers we didn't make mistakes. And we see now that we have an objective of 2000 that we had also given by the Excel solution. We used one mixed integer simplex iteration and 0 branch and bound nodes, and we have given the selection here for the items that we take with us, and we use the overall maximum amount of 100 kilos. And for the next exercise, I want you to do this at home and try that out. Try also if that are different formulations, if you can formulate it as a knapsack or an assignment problem. We have Eve and Stephen. They are new students at SDU in Odensee, and they decided to share a flat. Now they have a problem because they are both not so much into cleaning or householding in general, and they need to distribute certain tasks among them. So they have made an estimate about how much time they would employ for certain tasks that need to be solved. And well, Stephen is a natural talent in this, but the tasks should be equally distributed among them. So here, this is the time estimate of the different activities that Steve and Eve have estimated for the time they would need: grocery, shopping, cooking, dishwashing, and laundry. And now I would like you to solve this for them. We have seen now along this video that we can use integer programming for different questions and tasks that we want to implement in our models as well. But we need to be careful with them, because if we restrict our decision variables to a more limited number of values that they can take, then we require also the solver to make a more amount of calculations. And the more decision variables that we restrict more and more, the more we have an exponential growth in the difficulty and complexity of our problem that can have combinatorial effects. So it depends on the number of integer variables and or binary variables that we define in our model, and if they have a special structure. So integer programming problems, due to the restrictive way the decision variables are handled, are more difficult, more complex to solve than the linear version of them. Recall in our first lecture that we had the diet problem that we introduced, and the more and more we restrict our decision variables, the more we restrict also the solution space, which one could think that is a positive thing, because then we have less possibilities available for the solver. But this is not the case, because if we don't have lines that delimit our solution space, we are working with just points. So the way of describing our polyeder, which is the solution space, needs more information. So we need to introduce so-called cutting planes in order to describe the solution space more. And this is a work that the solver needs to do, or we can introduce them in our model as well. But this is too far for this point of time now. We could argue that, the solvers and the computational power becomes better and better, so solving also large integer problems is not a problem anymore, but we need to take into account that the more we add in complexity, the more computational power we need. We have seen that for integer problems, they have a special structure that can be used also to simplify problems. So it is not that we restrict if we restrict the decision variable to be integer or binary, that this is always evil to our problem. As we have seen with network-based models, they may describe very well our solution boundaries, and that would make it more easy for solvers like CPLEX or the Excel solver to find a solution. But if that is not possible, in our solvers there are also implemented algorithms that first look at the LP relaxation. So they relax the definition of the decision variable to be binary or to be integer, and to see in order to find an upper or lower bound of our objective function value, where we would land. And we could also use this approach to solve really huge integer problems by applying first the LP relaxation and then rounding those values of the optimal solution to the next integer value. But in this way, we would introduce errors, and that would then lead us to some pitfalls. So if we round it up, it might be that the optimal solution to the LP relaxation is not feasible when required to be integer, or that the optimal solution that we get in this way is far away from the optimal integer problem solution. So it is a workaround, but it is a quite dirty one. But if our input parameters are also affected with some uncertainty, then this might be a good way to go. A better way would be then to develop heuristics, so algorithms that would be close enough to the optimal solution, but do not come with the computational complexity of calculating the optimal solution. So if you have questions to integer programming, then I invite you to post them in our discussion board for session 7. And it is time also to ask you about the midterm evaluation of our course, so how we are doing so far and what do you think shall be improved with respect also to our new situation with respect to setting up e-learning activities. I would love to get your input via the survey that I posted on Blackboard. And then thanks again for listening to this video, and the next session will be on goal programming. And we will have chapter 8 of a Terha book that we will base on this, and this will be provided to you via Blackboard in the next few days. Thanks for listening.